of Dr. Jiang Zhang during 2021 to 2023 at the second library of the cryptology. In the first part, I'll introduce some necessary preliminaries. Currently, almost all known FHE construction follow the same paradigm introduced by Gentry.
Hello, everyone, and welcome to the fully-homomorphic encryption session, so efficient FHE. We have three really interesting talks, and I think he started presenting. Is there any way? Okay, great. So a few minutes before we start, but the first talk is going to be about fast blind rotation for bootstrapping FHEs. And the talk will be given remotely by Biwung Xiang. And I think we can start now.
Okay. Is the voice good now? Yes. Let me begin. Thank you for the introduction. I'm really excited to be here today to chat about some of the progress we made in FHE. The title is Fast Blind Rotation for Bootstrapping FHE. And this work was done while I was a resident student in the group of Dr. Jiang Zhang during 2021 to 2023 at the Silicon Library of Cryptology. The first part, I'll introduce some necessary preliminaries. Currently, almost all known FHE constructions follow the same paradigm introduced by Gentry. Firstly, construct a somewhat homomorphic encryption using the noise-based encryption. As you can see, for an encrypted ciphertext of M, the green part represents the noise. After performing homomorphic operations, we obtain an encrypted ciphertext of FM. However, at this point, the noise has reached its limit, making the ciphertext impossible to decrypt. Then we should design a bootstrapping algorithm that essentially homomorphically computes the decryption of somewhat homomorphic encryption for the first layer to reduce the noise size of ciphertext. We do not denote the ciphertext with full noise in the first layer as C and the secret as S. Bootstrapping is the process to homomorphically computing the inner product of C and S model Q. And it's well known that homomorphically computed the inner product is easy. However, homomorphically computing the model function is challenging. And the blind rotation is one of the key techniques to solve this challenge. The purpose is to homomorphically describe LW ciphertext on the exponent, and the input of the blind rotation algorithm consists of an LW ciphertext and a rotation polynomial and the evaluation K. The output is a ciphertext that results from the product of X to the noise M obtained after describing the LW ciphertext and the rotation polynomial based on the properties of power of 2 cyclotomic rings where X raised to the power of Q equal 1. The model cooperation can be done for free in the exponent. Moreover, by designing the form of the rotation polynomial, we can ensure that the constant of the message is exactly equal to M. And the exciting blind rotation can be divided into two approaches according to the underlying difficulty assumptions, RW-based and NTRU-based. The RW-based blind rotation has three competing methods. The AP method, which relies on the decomposition of A in some base B. supports all key distributions but need large evaluation case. The Jinx method, which relies on the decomposition of the secret key, only need small evaluation case, but it only supports limited secret key distribution. Recently, Lin et al. Had proposed a new blind rotation using atmosphere. Their new blind rotation supports all secret key distributions and also supports small evaluation case. And the exciting NTRU-based blind rotation can be regarded as the promotion of Jinx method on NTRU, which has the same limitation as Jinx. In fact, there are 3 types of key distributions, namely uniform, Cauchy, and ternary distributions. And many exciting FHE library use small binary or ternary secret for performance consideration. However, the literature has reported several attacks on exciting library using small secret keys. And we think it's of greater theoretical and practical interest to improve the bootstrapping performance for large secret keys. Here is our contributions. Firstly, we present a new GSW-like encryption based on the NTRU assumptions, which supports very fast key switching and fast external products. Then we proposed a new blind rotation use our NTRU encryption and run atmospheres. Our new blind rotation had performance particularly case. Then we use our new blind rotation to bootstrap an LW ciphertext, resulting in fast bootstrapping time and has a small evaluation case. Moreover, employing large key distributions led to an additional improvement of 17%. The next part, I'll introduce how to construct our NTRU-based GSW-like scheme. Firstly, we define 2 parameters tau delta depending on the encodings, namely Regev-like, DF-like, and CKSN-like. Then our scanner NTRU ciphertext is defined as the KDM form. As you can see that both the noise term G and the message U are divided by the secret F. This is essentially required by a KDM security assumption on NTRU. And our vector NTRU ciphertext under the secret F prime is not the KDM form. Our vector NTRU ciphertext is defined as a vector noise J divided by the secret F prime and plus the gadget vector times the message V. We define the homomorphic multiplication between the scanner and the vector NTRU ciphertext as the inner product between the decomposition of the scalar NTRU ciphertext and the vector ciphertext. To do external product, we only set the secret F equals F prime. And it only needs D multiplications in RQ. Moreover, in order to convert our ciphertext under the secret F into a ciphertext under another secret key F prime, we can set V equals F divided by F prime. It also only needs D multiplications. The next part, we describe our new blind rotation. First, we record the purpose of the blind rotation is homomorphically describe the LW ciphertext on the exponent, and to homomorphically compute x to a times s. We first use the atmosphere x is mapped to x to a to the ciphertext under the secret f. One problem is that the new ciphertext is not a ciphertext under the original secret key f. So we need to perform one case switch. And we design the algorithm. It comes practice to set the internal value of the accumulator to be an encryption of B. However, the atmosphere also affects B. So in order to counteract the influence of the atmosphere on B, we need to modify the form of the accumulator. Instead, we set the accumulator as x to the inverse A0 times B. And furthermore, to ensure that the same structure is maintained in the next iteration, we need to employ the atmosphere x to A0 times the inverse A1. So after n iterations, we finished our blind rotation. It totally needs n external product and n case switching. One problem is that not every AI has inverse. So to solve this problem, we can set Q equals n. Therefore, the x to 2 has order Q. And all the odd numbers less than 2n for a multiplication group. Additionally, within this multiplication subgroup, for any two elementals, their inverse and the products are also elementals of the same group. Then we can instead compute x to 2 times AI times Si equals x to Wi times Si times x to minus Si, where the Wi equals 2ai plus 1. This totally need extra one external product and one evaluation K. Also, we can extend it to the general case for Q less than n. Another problem is that in the previous scheme, the rotation polynomial times x to minus b can later treated as a noiseless scalar ciphertext. However, this feature is not satisfied for our KDM4 NTRU ciphertext. Fortunately, we can solve this problem by carefully design the evaluation key. In our algorithm, we designed the first evaluation key as the KDM form vector NTRU ciphertext. And the external product still satisfied, as you can see that the homomorphic operation between a polynomial U and the KDM form vector NTRU ciphertext, we can get a scalar NTRU ciphertext. Here is the comparison between our blind rotation and the RW-based blind rotation. As you can see that our blind rotation are the best blind rotation in terms of computation efficiency and the storage. The next part is the bootstrapping. First, let me overview the bootstrapping in TFT and FHEW. Firstly, the ciphertext of the first layer is an LW ciphertext with a models of small q. After the blind rotation, it becomes an LW or TLW ciphertext corresponding to a large models q. Then, through the simple extraction, a new LW ciphertext under the BQ is obtained. Finally, we perform once key switching and the model switching to get a refreshed ciphertext. The key difference in our bootstrapping algorithm compared to the framework mentioned above is that after applying our new blind rotation, we obtain an NTRU ciphertext. Now the next step is to transform this NTRU ciphertext into an LW ciphertext. We have observed that the NTRU ciphertext can essentially be regarded as an LW ciphertext with B equal to 0. Therefore, we can achieve this goal by employing a straightforward simple extraction like this. And we can extract the LW ciphertext with B equals 0 from the NTRU ciphertext. Okay. Finally, we present the result of our experiment. And the two sets of parameter choice corresponding to the ternary king and the Cauchy kings for the first layer respective. For parameters with ternary king distribution at 128 bit security, our bootstrap time is about 3.2 times faster than FHEW and 2.1 times faster than TFT. By using the Cauchy king distributions, we can obtain an extra 10% improvement. And for 192-bit security, our bootstrap time is about 3.7 times faster than FHEW and 2.7 times than TFT. Also, we can use Cauchy king distribution to improve the performance. Finally, we summarize our work. Firstly, we proposed an NTRU-based JSON-like scheme with fast internal product and case switch. Then we use our NTRU-based scheme to design a new blind rotation, which supports the arbitrary secret distribution and has small emergence case. Then we use our blind rotation to bootstrap an LW ciphertext, resulting in a faster bootstrapping. And we can improve our parameters by using the Cauchy distributions. And we believe that the large secret distribution offers better security. That's all. Thank you.
So we have time for a quick question. Nadia.
Hi, can you hear me? Can you hear me?
I can.
You can? Okay.
Yes, I
Thank
can.
you so much for your presentation. I have just a quick question about your comparison. So you said that you're faster than TFHE, but the state of the art on true is the final scheme. So I wanted to ask you how do you compare with final, which is the other true-based scheme? And also, I just wanted to know, are you doing gate bootstrapping, from what I understand, right?
The question is to compare to final?
Yes.
Okay. Wait a minute. In terms of constraint inventions for binary key distributions, our performance worse than final. But for ternary key distributions, our performance is equal to final. And for bigger key distributions such as uniform or cost, our performance is better than final.
Okay, thank you.
Yeah.
Okay, let's thank the speaker again. An application to transciffering, and this talk will be given by Hae-Yoon Park.
Okay, thank you for the introduction. Hello, my name is Jaehyun Park. Jaehyun Park from Seoul University. So today I'm going to present ERMAS, which is a efficient ring packing algorithm for FH ring packing and its application to transciphering scenarios. So this is joint work with Youngjin Bae, Jung-hee Chun, Jaehyung Kim, and Damian Stella. And Jaehyung is also here in the room. So let me start with, so here's some like brief overview of this talk. So we focus on we consider some ring packing problem for a fully homomorphic encryption setting. So we call this as FH ring packing problem. So we first suggest a generic acceleration tool for FH ring packing algorithms. And after that, we will propose a new FH ring packing method, which we call ERMAS. So compared to the state-of-the-art work, ours achieve like more than 40% higher, more than 40 times higher throughput. And we also apply this ERMAS to the transciphering scenarios. So let me start with the motivation and definition of ring packing. So as you are probably aware, fully homomorphic encryption is a crypto system that enables homomorphic computation on encrypted data without any decryption. So there have been several FH schemes for decades, and we can roughly categorize the FH schemes into two categories. The first one uses LW format. So in this setting, each datum is encrypted to a single ciphertext. So we can have some high level of granularity. So TFHE or FHEW schemes are based on LW format of ciphertext. But so if there are like a few messages to manage, then LW formats like provide fast latency. But if there are like lots of data, then the throughput is not that very satisfactory. So the other one uses like ring LW format. So in this case, like a number of data or several data are encrypted in a single ciphertext, and we can obtain like high throughput. So BGP, VFB, or CKK schemes are based on ring LW format. And in this case, like we can have high throughput, but if there is a few messages to manage, then the latency might be not that efficient. So since each format have some different strengths, the natural question here might be, is it possible to efficiently convert the scheme, the format? So hopefully the converting ring LW format into LW format is quite straightforward and a bit more easier, but the opposite direction, packing ring LW format into a ring LW format is quite a bit more challenging, and we call this problem as ring packing problem. Okay, so if there exists an efficient ring packing algorithm that might bridge LW and ring LW format, right? So that means like when we perform some homomorphic computation, so during computation, if we want some high level of granularity, we can use LW format, okay? And once we need like high throughput, require high throughput, then we can switch the format by using ring packing and continue the homomorphic computation using like ring packing. Okay. So they're having like several works on ring packing problem. They propose like great algorithms, but at this moment, like it was really difficult to compare the existing ring packing algorithms apple to apple. So to understand this, let me briefly explain the general structure of ring LTB-based FH schemes. So they are usually like level homomorphic encryptions. So that means like we are considering a chain of moduli like this. So the fresh ciphertexts are located in this high modulus, which I call QComp. And during the homomorphic computation, we consume some moduli. And once we go to the bottom, once we reach the like lower moduli, here I say like Q refresh, we perform bootstrapping and we recover the modulus and go back to QComp and continue the homomorphic computation. So previous works on previous ring packing algorithms output like ring LTB formats with different modulus. So some ring packing algorithm output like ring LTB format of QComp, and some output ring LTB format with Q refresh, modulus Q refresh, and some outputs like in between. So it was really difficult to compare them apples to apple. And also some similar things happens also for the other parameters, like they are like targeting on different ring degree or some encoding structure of ring LTB format. Okay, so in this talk and in our work, we focused on ring packing for FH fully homomorphic encryption setting. So when do we need like ring packing? So usually we mostly desire like right after ring packing, we want to perform some homomorphic computation with high throughput, right? So the most desirable output might be like the packing into the ring LTB format be like sufficiently large modulus. So basically we are targeting on like outputting ring LTB format of modulus QComp, the highest modulus we can think of, and with some sufficiently large ring degree that we can do some bootstrapping procedure. Okay, so this is our targeting fundamental or problem, and actually like so what FH ring packing means that we want to output some ring LTB format with large parameters, right? So there is some challenges like since we want to output some ring LTB format on the QComp, that means like we should like do ring packing above the QComp modulus. So it turns out to be like unsatisfactory running time and also key size, because usually computation with large parameters is much slower than the computation in smaller parameters. So the computation is like really slow to be used for practice. And also the key size was like pretty large since we are working with like large parameters. Okay, so we will gonna address this issue and accelerate the FH ring packing algorithms. So first, I wanna optimize the modulus part. So conventionally, what we do is like to output a ring LTB format in the QComp, we conventionally do ring packing with the large modulus, right? So instead, we will optimize the modulus by doing everything in the lower modulus. So here, that means like here, instead of doing FH ring packing, we're like thinking another problem based ring packing that outputs ring LTB format with like the smallest modulus as possible. So by doing that, we can do the ring packing in the bottom modulus, and that will like accelerate the process by a lot. And after that, to obtain the desirable ring LTB format, we do bootstrapping or some part of bootstrapping, and we finally finish the ring packing, FH ring packing procedure. Okay, and also by doing everything in the smaller modulus, the key size would be also like decreased by a lot. Okay, and also here, I also want to point out that this kind of like aggressive moduli optimization is not that very conventional. So in the FHE application scenarios, like it is like prevalent to schedule the computation to optimize the modulus, but usually we don't really consider some extra bootstrapping, because like bootstrapping is much slower than homomorphic other types of homomorphic computation. So for example, for CKKS, like the bootstrapping is like 100 times slower than a single homomorphic multiplication. So we usually do not consider any like extra bootstrapping for the moduli optimization. But here, since ring packing is really a massive circuit, so here what I mean by massive is like, so ring packing is as massive as bootstrapping circuit itself. So the advantage of doing this massive ring packing circuit in the smallest modulus is much larger than the cost of single bootstrapping. So this is why this aggressive moduli optimization works for FH ring packing scenario. Okay, all right. So now let's go to the another parameter. So even with our moduli optimization, we still suffer from some high ring degree of ring algebraic format. Okay, so this is because we are targeting on FH ring packing. But actually, since we are working with the smallest modulus, actually there are like much room for security level, and also there could be a chance to do everything with the smaller ring. Okay, so to do that, we adopted ring switching technique. So by using ring switching, we can switch the small ring of ring algebraic format to an external ring with higher degree. So with this ring switching technique, here's our strategy. So instead of doing everything with high degree of ring, we first do ring packing to a smaller ring of ring algebraic. And after that, by using ring switching, we combine them all together, and we get a ring algebraic format with high and sufficiently large ring. And after that, we can do bootstrapping and we can do everything. Yeah. So by doing this, we can like, so that means like we can use a smaller ring degree, and so that means like the ring packing procedure will be accelerated further, and also the key size will be like further decreased. So this is like good. So here's some brief sum up. So conventionally, when we are considering FH ring packing, it was conventionally like we do everything with really large parameters to output a desirable ring algebraic format. But instead here, we optimize everything, every parameters, and we do everything with the smallest parameters, and that accelerate the procedure and also decrease the key size by a lot. And after that, we use like ring switching and some bootstrapping to finish the complete FH ring packing. So this is a generic acceleration tool for FH ring packing algorithms. Okay, so now let's accelerate the existing works by using our acceleration tool. Okay, so before doing that, let me briefly say what we technically do when we do ring packing. Okay, so ring packing means that we want to pack LW ciphertext in a ring LW ciphertext, right? So for a given LW ciphertext, that means like we are given a vectors that satisfying these approximate equations. And also you can easily think that this is actually a linear system with errors. So this is like a plaintext, plaintext matrix and ciphertext vector multiplication. So what we technically do for ring packing is usually we just assume that we are given a ring algebraic encryption of this vector, and after multiplying this by the plaintext matrix here, we can get a ring algebraic encryption of message. So this means that we did some ring packing. We finished the ring packing procedure. So in short, ring packing is a multiplication between matrix, the plaintext matrix and ciphertext vector in ring algebraic formats, technically, yeah. So with this background, now we can roughly like categorize the existing works into 3 approaches, depending on the encoding structure of the plaintext matrix. Okay, so the column method, so for example, the column method encode each column of the plaintext matrix, and row method encode each row, and diagonal method encode each diagonal. Okay, so at the first glance, the row method and diagonal method looks really efficient and good in terms of both running time and key size. But here I want to point out that the column method doesn't consume modulus during ring packing procedure, while the row method consumes a small amount of modulus, and diagonal method consumes lots of modulus during the ring packing procedure. So this makes a difference when we accelerate each method by using our acceleration tool. So when we accelerate the column method, then we can really select the extremely smallest parameter. So that means like we can accelerate everything really extremely. And when we select the roll method, we can do pretty good, but not as extreme as the column method, because since it consumes some modulus during ring packing procedure. And finally, when you try to like accelerate diagonal method, it's not that easy because it itself consumes moduli during ring packing by a lot. So the less moduli consumption was better to apply our acceleration tools. And after our full optimizations, we found that column method was the most effective. Okay, so for the rest of talk, I'm gonna mostly focus on the column method. Yeah. So let's go for Hermes or proposed method. So actually the Hermes Gero is nothing but the column method with our full optimizations. Okay, so let me be a little more specific here. So here is some plain text vector and ciphertext plain text matrix and ciphertext vector, and we want to multiply this, and we are encoding each column of plain text matrix. Okay, and so actually here's some like a cute linear algebra. So actually the matrix vector multiplication is a sum of vector scalar multiplications. Okay, so then if we are given a ring algebra encryption of each scalar, then by using some technique we say key switching, we can squeeze the column, and after squeezing the column, we obtain a single column, which is a ring algebra format, which means we finish the FH ring packing here. So this is practically fast. Practically fast is good. But however, since we need like all encryption of all scalars, so that means like we need like lots of encryptions, and the key size is still too large, even with our full optimizations. Okay, so to address this issue, we also propose a Blanc method. So in this case, we don't really encode column or row or diagonal. Instead, we encode the submatrix, the block of the given plain text matrix. Okay, so after that, we can also think a Q linear algebra again. So, and after that, instead of like squeezing the columns, here we squeeze the blocks, the Stribov block. And after that, after the squeezing, we obtain a squeezed matrix. And after we squeeze it again to become a single column, and this is our Blanc method, how our Blanc method works. So basically, Blanc method is slightly slower than the column method, but not that significantly. And also here you can see that we can efficiently use the switching keys. Okay, so for example, here there are two strips, and for each strip we can use the same key to squeeze for squeezing, and it just simply decreases the key size by a lot. Yep. So this is our Blanc method, Hermes-1. And some may wonder how to encode the blocks and how to squeeze the blocks, right? Because it is counterintuitive to encode block into ring LWE formats. So to do that, we adopted modular LWE, MLWE formats, and to squeeze the block, we introduced modular LWE key switching and modular LWE ring switching in our paper. So please see our paper if you're interested. Okay, so let me explain the experimental results. So compared to the state-of-art FH ring packing, the Pegasus, which is a diagonal method, ours obtains like more than 40 times higher throughput. Okay, and also I want to like point out the key. Point out the key size here. So comparing Hermes Gero and Hermes-1, the column method and Blanc method with the same parameter, the Blanc method was like slightly slower, but not significantly, while the key size was like much more smaller. Okay, and also we could like applied our RMS some ring packing algorithm to transciphering scenarios. So basically, when we transmit or store the ciphertext, we usually want some like high level of granularity, right? Okay, so for example, I want to send to Bob a single data, but if we are using ring RWA format, that means like we need like really like big size of ciphertext. So to address that, like we can simply send the ciphertext using LWA format, and after that, right before perform some homomorphic computation with high throughput, the server can simply ring pack by using RMS to make it into a ring RWA format. Okay, so that is how we can like solve some problems in this transciphering scenario. And here is some comparison between the latest works on transciphering into CKKS scheme, which is a ring RWA format FHE scheme, and compared to the Hera and Rubato, ours like saves lots of like server-side cost. Okay, so just let me wrap up. So we optimize the existing ring packing method for FHE. And also we propose a new efficient FHE ring packing method, which we call RMS. And it was like compared to state of the art, it was like 4 times faster in terms of throughput. And also we applied this to transciphering. Thank you.
So we have time for a few questions.
Thank you very much for the nice talk. So you mentioned that you try to use a smaller parameter during like a ciphertext conversion to minimize the key size, but in a large scale, if we anyway need a bootstrapping key to refresh the ciphertext after conversion, the bootstrapping key involves like a rotation keys with a larger parameter. So does your optimization really bring some advantage in terms of total key size?
Yeah, so I think that's really a good question. So the question was that like since we want to do some bootstrapping, the key size might be like dominated by the key size for bootstrapping, right? So that is true, but so that is true, but even with so here's some numbers for that. So for bootstrapping, so in our experiments, like half of the bootstrapping key size was like more than 600 megabytes. But even with that, I think like RMS0 is not, the key size for RMS0 is not, I mean, not really negligible. So maybe I think like RMS1 have some advantage compared to that. And also, as you said, row method and diagonal method might have some advantage because they are using rotation keys. But for example, in the diagonal method, some rotation keys are not really necessary for the bootstrapping, so maybe they is not really that effective. And for the row method, so they can be used because they are rotation key, but still like some might not be really necessary for bootstrapping. So yeah.
Okay, thank you.
Any other questions? Okay, so I think we can thank the speaker again.
Can you hear me? Okay, perfect. Hi, hello everyone. My name is Young Song from Seoul National University, and I'm gonna talk about some general optimization technique for homomorphic encryption operations. And this is a joint work with Miran Kim, Dongwon Lee, and Jin Young Seo. I can see that you pretty much enjoyed yesterday's party, so I will try to make my talk simple and to the point. So, as you know, after the Gentry's first construction of a fully homomorphic encryption in 2009, this technology has evolved very significantly in the last decade. So several schemes were designed and like optimized and implemented by academia and industrial companies. And then actually we achieved like an amazing speed up during this period, even much faster than most law. But the recent studies are more focusing on like some other topics, such as efficient bootstrapping method or design of threshold and multi-key homomorphic encryption schemes, or some advanced functionality to support non-arithmetic operations or their applications in machine learning. So now the community is considering some other directions to overcome the limitation, because there has been no fundamental, unfortunately, there has been no fundamental improvement of HE algorithm in the last few years. So in 2021, the DARPA launched what's called the DEPRIVE project, which stands for Data Protection in Virtual Environments. They choose 4 teams to develop some hardware accelerator optimized for FHE computation to make some dramatic performance improvement compared to software approach. So this is the current status. But in this talk, we say that there's still room for algorithmic improvement. And our primary goal is to accelerate the external product, which is a common building block of homomorphic encryption schemes to reduce the noise growth. And it is a key building block of most of non-linear homomorphic encryptions, homomorphic operations, including key switching, multiplication, automorphism, or bootstrapping. And this, our contribution is the follows. We present a new external product algorithm achieving better asymptotic and concrete performance. And another advantage is that our method is surprisingly simple and compatible with the prior method. So you don't really need to like re-implement everything from scratch, but you can simply reusing the existing libraries and add on our method without too much effort. Okay, so my talk consists of 3 parts. I'll first give some simple overview of gadget decomposition and define external product. And then I'll introduce the state-of-the-art external product method. And finally, I present our solution with its performance analysis. All right. So we'll use this standard notation, R and Q, to denote the ring of integers and ciphertext modulus. And the gadget vector is some fixed d-dimensional vector. Its entries are G0 to Gd-1. And these GIs will be called the gadget bases. And we basically consider the linear combinations of these gadget bases with some coefficients xi, where these xi's are elements of the ring of integers. And this linear combination is well, oops, sorry. Yes, and this linear combination is well defined because RQ is basically R module. Right. So the gadget decomposition H corresponding to gadget vector is a function from R mod Q to R to the D. The idea is, roughly speaking, we would like to represent an arbitrarily elements of RQ as a linear combination of gadget bases, where its coefficients are like a small elements of R. So more formally, for given elements A of RQ, we aim to find some like this vector H of A, such this is a short vector over R, such that the linear combination of this GI with the coefficient BI is equal to this input element A mod Q. And the classical example that we used like about 10 years ago is called the base decomposition. So for a base integer B and some degree D, the gadget vector is simply defined as a powers of B, and then this decomposition function is simply defined as a base B representation of A, such that like A is a summation of a BI multiplied by B to the I. And you can easily check that by definition, it satisfies this primary condition for Gaussian decomposition, and the bound of this decomposed vector is also bounded by B. Right, the external product. So this external product is like the originally proposed in this CGI TF paper by TFH team to like describe some multiplicative operation between ring LWE and ring GSW ciphertext. But in this talk, I will use the same terminology to refer to some more general operation defined as follows. So the external product is a binary operation between some like one element of RQ and a d-dimensional vector over RQ. And then for input A and input vector U, we return just a single polynomial C. And this external product consists of two steps. In the first step, we first compute the Gaussian decomposition of this A and obtain its decomposition like these BIs are small coefficients. And then in the second step, we compute the linear combination of this UI with coefficients BI from the first step. More generally, if you are given some like a matrix consisting of two columns, I will just abuse the notation and denote the external product between A and U by like the pair of two polynomials obtained by obtained from the external product between A and U0 and U1. So this is the definition. The main application of external product is secure multiplication of a scalar. So you can basically realize the secure scalar multiplication using this external product operation as a building block. So to be precise, suppose that you're given a polynomial A and matrix U. So this matrix U is ring LW encryption of some plain text T multiplied by Gaussian vector G. So basically, this is like a bunch of ring LW encryptions encrypting T times G sub I. So if you take an external product between A and U, you obtain this pair of polynomial from the definition, and which becomes a valid ring LW encryption over A times T, because if you decrypt this ciphertext using secret key, it returns like a decomposition of A times T times G plus some error, which is approximately equal to A times T. So basically, you multiply this T securely to the given element A here. So another direct application of this external product is called the key switching procedure. This is a common building block of nonlinear homomorphic encryptions, including homomorphic multiplications or like a homomorphic automorphisms. In CKCS, for example, if you multiply two ciphertexts, then you obtain a triple of polynomial, which is decryptable by 1 S and S square. So you need to linearize this third element to recover the canonical form. So in this case, you can simply use this operation. So the linearization key can be viewed as a ring LW encryption of S square times Gaussian vector. And by multiplying this U to the third component of a ciphertext, you can linearize the component. In other case, for automorphism evaluation, you again need the ring LW encryption of a phi of S, where phi is the automorphism you want to evaluate. So in practice, this external product is a major complexity bottleneck of homomorphic operations. It usually takes about 85 to 95% of total computational timing. this is one example. Like CKK multiplication consists of a simple tensor product followed by linearization process, and linearization takes most of the time in homomorphic multiplication. So that's exactly what we want to improve in this one. Okay, so let me show you how the state-of-the-art libraries are implementing this external product. We are basically using this RNS, reduced number system. So the ciphertext modulus is chosen as a product of distinct primes so that we can take advantage of this Chinese remainder theorem to represent like this large polynomial A as a tuple of this polynomial A modulo Qi. And we also use what's called entity, which is a DFT over this prime field. So if this individual prime factor satisfies a good condition, then there exists some primitive root of unity. So we obtain this ring isomorphism. So in this entity space, polynomial multiplication can be done very efficiently using just component-wise multiplication. So, but still, we sometimes need a coefficient representation. So entity basically behaves as a conversion between these two representation between coefficient and entity form, and the complexity is n log n operations over this finite field. So this is the most expensive union operation in homomorphic operation. All right. So in practice, we use what's called the RNS-based Gaussian decomposition, which is very efficiently implementable over like RNS representation. So the ciphertext Q is again the product of prime numbers as usual. And this Gaussian vector is defined as the vector of CRT constant, meaning that like i's component GI is congruent to 1 modulo QI, and this is multiple of other all other primes QJ. So this RNS-based decomposition is simply defined by like the tuple over A mod QI. And it is easy to show that this function is actually a valid Gaussian decomposition corresponding to this CRT vector, thanks to the Chinese remainder theorem again. And its bound is also quite small because these entries of this decomposition is bounded by like a word size prime QI. So the thing is that one good thing is that this decomposition is RNS friendly, meaning that we don't need a multi-precision, but we can stay in the RNS representation still able to compute this decomposition. But on the other hand, this decomposition cannot be computed in the entity form, but we should first convert the polynomial into the coefficient form to obtain this, to compute this decomposition. Okay, let me recall the definition of product, which consists of a decomposition followed by linear combination. And the key question is how to implement the product of these two elements, BI and UI, because BI is a small element in the ring of integers, while this UI is like a large polynomial, polynomial in a large integer modulo QI. So in the existing libraries, what we are doing is that we first compute the RNS representation of BI, meaning that we take a BI modulo QJ for every pair over I and J. And then we perform the inner product over this R mod Q, because after this transformation, we now have two vectors over the same space RQ. So now we can take an inner product. But actually, this first step is very expensive because the conversion from elements of R into R mod Q requires a lot of entity conversions. Because for each BI, you need to first take a coefficient form of BI, and then take entity modulo QJ to obtain its entity form before multiplying to this UI. So we require entity conversions for each of a BI, so D square in total. And the actual multiplication between this B mod Q and UI mod Q is relatively simple because it requires D square multiplication over unit complexity big O N. Okay, so now let me introduce our approach. So our primary goal was to optimize this linear combination. And we observed that the prior method had a performance bottleneck in conversion from BI into the RNS representation with modulus Q. So our idea is that what if we perform as much as computation over the ring of integers instead of converting this BI to R mod Q? But the second input, UI, these are elements of RQ, not elements of R. So maybe we should come up with another method to represent this element UI using some elements of a ring of integers. And actually, we already know a quite nice method to represent on arbitrarily elements of RQ using the elements of a ring of integers, which is exactly the Gaussian decomposition. So let's suppose that we are given the decompositions of UI instead of simply UI. So meaning that H of UI is written as a tuple of V I comma J, where UI can be written as a linear combination of these Gaussian bases with small coefficients Vij. Now Vij, these are small elements of ring of integers. So if you plug in this equation into this definition of C, external product, and manipulate this equation, so this UI is, roughly speaking, this C is a linear combination of UI with small coefficient BI, and each UI is again written as a linear combination of Gaussian bases GI, GJ with a small coefficient Vij. So this equation can be rewritten in this way, so that this linear combination can be written as a linear combination of Gaussian basis GJ, where its coefficients can be written as some equation between BI and Vij. So the coefficient of so the output is a linear combination Gaussian basis with coefficients Cj, and some properties are the following. As I already explained, Vij can be pre-computed because UI is usually some component of an evaluation key. So these are not ciphertext components. So we can pre-compute the Gaussian decomposition of key switching key beforehand and just store it in a different form of key switching key. And then this coefficient Cj can be it's just the equation between Bi and Vij. And these are all small elements of a ring of integers. So we no longer need a computation over R mod Q for large integer Q, but just this inner product can be computed over this ring of integers. The output is just a small element of R, and it's bound, or equivalently, the required precision of DFT to compute this product is basically determined by the Gaussian decomposition we are using. So for example, if we use like a single precision Gaussian decomposition, then this Cj may have a double precision because it's a product of two single precision polynomials. And finally, we need to compute this linear combination over Gj with the coefficient Cj, but this is actually unnecessary because this tuple of Cj is already gives you the RNS representation of desired value C, because these Gj's are like a Gaussian basis satisfying some good CRT properties. C is simply congruent to CJ modulo QJ. So once you obtain all these coefficient CJ, you already obtain the RNS representation of C. That's the final output. So to sum up, if you have two input A and vector U, then we pre-compute the decomposition of UI, and then even we pre-compute its DFT form over the ring of integers. And in real algorithm, we first compute this decomposition and take a DFT over R, which requires D DFTs. And then computation, the multiplication is followed. It still requires D square multiplications over the DFT space. And finally, each coefficient CI, CJ, should be converted back to the coefficient form, which requires D inverse DFTs. And finally, you can just take CJ mod QJ to obtain the RNS representation of C modulo Q. So you can see that this is a purely algorithmic optimization, meaning that even if we use like a different algorithm, the output ciphertext is exactly the same as before. So there's no like disadvantages like noise growth or any other issue, because it exactly the same outputs the same ciphertext. Okay, so these are some like optimizations and generalizations that I'm not going to explain full details in this talk, but in our implementation, we use the more general RNS decomposition where you can actually use arbitrarily like D0 to D-1 as a CRT basis, and the Gaussian decomposition is defined by just a tuple of A modulo DI. In practice, this each digit DI is usually product of a fixed number of like a single precision primes. In practice, it's usually some number between 1 to 4. And secondly, we also apply like a special modulus technique. If you use a larger decomposition size, then the noise of external product grows together. So it is required to combine with this special modulus technique, where the key switching key is generated in a larger modulus, and the external product is mostly computed over this larger modulus, and finally the modulus is switched back to the original modulus Q to further reduce the noise. But in this case, the key switch key has a larger modulus Q prime, which is P times Q for some special modulus Q, special modulus P. So we need to introduce another decomposition H prime to decompose this key switch key with a modulus Q prime. And this decomposition may have a different digit size R prime. And finally, we need a multi-precision DFT over R. And this precision depends on this decomposition size R and R prime. Because if you recall the previous equation about C, the coefficient was represented by some inner product between Bi and Vij. And Bi, the size of Bi and Vij are determined by these parameters R and R prime. So you need to implement like sufficiently large precision DFT to guarantee the correctness. So in implementation, we use the Go language. So our algorithm was implemented on the top of a Letigo library. And for parameter setup, we consider the most widely used parameters. The dimension is 2, 3, 15, and 16. And for each parameter R varies from 1 to 4. We ran the experiments to choose the best R prime for each R. And to implement the ring of integers, we just instantiated this ring of integers using just R mod B for some sufficiently large B, so that no reduction modulo B happens during the computation of this inner product. So B is again a product of a few primes. So a single DFT over this ring of integers corresponds to a small number of entities in our implementation. So these are some benchmark. You can see that for like this decomposition size of a ciphertext, we tried to find the best optimal I prime for key switching key decomposition. And we achieved a speed up like about from 1.5 to like a 3.3, depending on the like a gadget levels of ciphertext and the size of gadget decomposition. And as I mentioned at the beginning of my talk, so linearization takes most of time in homomorphic multiplication. So homomorphic multiplication consists of a simple tensor product followed by linearization. We still have the same complexity for tensor product, but we significantly decreased the complexity of this linearization by a factor of about 3. And if you take a look at the profile of this complexity of our key switching, you can see that you can observe that previously, like the complexity of linear external product was dominated by the entity operations, because the entity operations has like a n log n unit complexity. But in our case, since we reduced the complexity from n square entities down to d DFTs, now this DFT takes only a small portion of a key switching operation in implementation. And another observation is that previously, it was very important to use a slightly larger decomposition size to reduce the multiplication timing. But in our case, the timing still decreasing, but not significantly. So there is no strong motivation to use a larger decomposition size, because a smaller decomposition size provides a better computational capability. Okay, to conclude, we developed the novel external product algorithm, and we made both asymptotic and concrete performance improvement. So in terms of asymptotic complexity, our complexity is reduced from d square entities and d square multiplication down to d DFTs and d square multiplication. So previously, this part was dominating, but now DFT takes less time, but d square multiplication has become the dominating term in our implementation. So in terms of a concrete performance, we achieved about 3 times speed up, and our implementation is compatible with the existing method, because we can simply reuse the same key switching key, but just a pre-computation is required to obtain its decomposed form. And another advantage is that our method is quite hardware friendly, because usually this entity, sorry. So usually these entity operations were considered a major bottleneck in hardware implementation, because other operations like Hadamard multiplications or inner product are easily parallelizable, but the entity is not. But in our case, now these square multiplication parts are dominating a factor, and this simple Hadamard multiplication is very easily parallelizable and hardware friendly. So I believe that our paper will affect, for example, the DeepRive project to develop some efficient hardware accelerator for FHE. Okay, thank you for listening. And our paper and source code is publicly available. And yeah, thank you. And I'm happy to take any questions.
We're a little bit over time, but if there's a quick question, or is everyone ready for lunch? Okay, I guess we can thank all the speakers of the session again.